好像比他们小，他也就感觉有2、3年级的时候，3、4年，可能是3、4年级的吧，我也不太清楚，反正看着比他们小。
Not in that one class, but like in a different class. Sadly, yeah. Wait, why do I have this? Wait, Daniel. I don't know. Hey, Daniel, recognize this? Chinese form of currency. No, and like metal. That's a copy. I got mad and I started punching so English.
Okay, guys, let's start. So first, let's kind of go through the homework problems I assigned last time from the first section, right? 5.1. Do you have any questions about those? Or just kind of go through them real quick. So it's on page 181. So remember, I assigned the even problems, right? And also on page 184. So actually all even problems. Okay, so we can just go through them really quick. We haven't done that. Okay, so on page 181, 5 to 200. Okay, so this one is pretty easy, right? So we have the angle measure of healing triangle are x, 2x, and 2x plus 15. So what's the measure of the smallest angle? Well, so basically you ask about x, and there, if you're adding all of them up, you should get 180, right? So that's a very easy one. So for x, you get x equals, so what's the answer? 33 degrees, right? Pretty straightforward. And the next one, 5.400. So we have a regular decagon, which is basically 10. So we have 10 sides, right? It's a regular 10-side polygon. Then what's the measure of the angle ACB? So this is A, B, C, D, etc. IJ, so this is for J and I. I won't draw the whole thing. But you ask about the angle ACB, right? So not ABC, but ACB. So this angle here, right? So how do you find this angle? It's called theta. How do you find theta? Yes.
Since angle ABC is isosceles.
So it's isosceles, right? So then if you can figure out this angle, right? So what is angle B?
1440 divided by 10 is 2044.
Okay, so basically it's n minus 2. So it's 10 minus 2 times 180, then divided by 10, right? So what's the answer? 444? 144 degrees, right? Okay, so 144, then basically theta would be 180 minus that, divided by 2, right? So the answer for that one is 18 degrees. Is that everyone done? So it should be pretty straightforward, right? So next one. For the next one, we have a regular polygon has interior angles measuring 179 degrees. Okay, so we have an interior angle. So this is 5.600, right? So you have interior angle is measured as 179 degrees, and then we have a side length is 2 cm. Right? So this is a regular polygon. We're not sure how many sides are there, right? So you just know that it's a regular polygon, and they're asked about what is its parameter, right? Okay, so how do you solve this kind of problem? How do you decide how many sides are there for this polygon?
If the interior angle is 179, let the number of sides be x.
Yeah, let's call it. How about n? N is better, right? So again, we can call it x. Yeah, let's go with x. It doesn't really matter. So let's say it has x sides, right?
And then if it has x sides, then x minus x, x 180, x minus 360.
Wait, so the total number of, so we have x sides, so basically there are x interior angles, right? So then one of them is 179. So if you add all of them up, you should have 179 degrees times x. Right? That's only one hand. On the other hand, if you add up all the interior angles, how many degrees you have?
60 plus 180x.
So it's n, not n, x minus 2 times 180, right? Okay. So then, if we set up the problem right, this should be the equation to solve.
Can you do 180 minus 360 over x equals 179? Yeah.
Oh yeah, you could also do it that way. But I just prefer to set up equations because I'm used to it. Anyways, you find x equals what? So how many sides are there? Should be 360, right? Yes. So then there are 360 sides. Each side has length 2. So the parameter would be 360 times 2, which is 720. I mean, that's very good. You have your own way to do it. So normally for geometry problems, there are several ways to do it. And they're often just equivalent to each other. Okay, but feel free if you have another new way to solve it, or maybe a shorter way to do it. Okay, so it's 720 is the answer. Okay, and then 5.800. So we have a star is a decagon with 5 acute interior angles, right? So just draw a star here, just like this. Okay. So it has 10 interior angles. So 5 of them are acute angles. 1, 2, 3, 4, 5. Right? So the others are obtuse. Okay. And you ask about what is the greatest number of acute interior angles in any decagon? So I want the greatest possible number, right? Greatest number of acute angle. So how do you solve this kind of problem for a decagon? Right? Polygon with 10 sides. So how do you approach this kind of problem?
You make as many angles that are 89.9 degrees.
Okay, so basically, yeah. Okay, so you're trying to get this as close as to 90 degrees as possible, right? And then try to see how many. So first of all, we can't have too many acute angles, right? So we have. So what's the interior angle for a decagon again? So it's 10 minus 2 times 180. So this is 1,440 degrees. Okay. So in this problem, I'm actually looking at this the inverse way, so the other way. You might consider about this in this way as well. So instead of looking at the acute angle directly, I'm looking at all the obtuse angles. Obtuse angles. And see, so basically, I want to take as many angles as possible out from the obtuse angles, and then see how many acute angles can share the leftovers. Okay, so that's another way to do it. So if you think about it, how many acute angles can we have? You can't have too many, right? Because obtuse angle is pretty big angles, right? So if you think about it, in any kind of polygon, what's the biggest possible obtuse angle you can have? So this is any polygon, not a convex polygon, right? So it could look like this. So what's the biggest possible obtuse angle in any kind of polygon? So it could be as big as like maybe 359 degrees, 99, 99, etc. As long as it does not hit 360, right? If it's 360, then it's just a line, it's not an angle anymore. I just go back to itself, right? So what I mean is you could have an angle, something like this, right? So this is a very big angle, very close to 360, right? Okay. So I'm asking you the question, how many obtuse angle can a decagon have at most? Ten? Are you sure?
8.
So you can think about 360, right? Just keep in mind it's a little bit less than that. So if you have 10 of them, it's already 6,000 and some degree, right? So you can't have too much.
Something like 8.
8? Can this one hold 8 of them? So if you multiply 360 times 8, I don't know. I don't want to compute this number, but I'm sure it's definitely bigger than the total number. It's a lot less than you think. And how about we try 3 first? Okay, so let's try 3 obtuse angles. So how many degrees roughly does 3 of them take if everyone is at its maximum, close to 360? So it's going to be 360 times 3, which is how much? 1,080. Okay. And then you can see how many degrees are still left. How many degrees we still have? We have 1440 minus 1080, right? Which is that 360? So 360, right? How many angles do we still have left? If we take 3 of them to be obtuse, then 7, right? 7 of them. Okay. So 7 of them divided by 360. On average, we would have each acute angle to be maybe 50 something, right? 51 degrees. So it seems like we can do a little bit better, right? Because we still have some room for the acute angles, right? So how about 2? Can we do 2 obtuse angles?
Yes.
Yeah? Okay. So let's try. How many degrees do we have? If we have 2 obtuse angles, they have 360 minus 2 times 2 would be 720, right? Okay, so now if you subtract a little bit less than 720, right? So if you subtract 720 from 1440, what do we have? Also 720, right? But now we have a problem. Did anyone see the problem? Yes, because we write down 720, but in fact it's actually a little bit bigger than 720. Tiny little bigger than 720, right? But at the same time, we only have 8 angles left. So if you want to make all the 8 to be acute angle, 8 times 90 is 720. And we have to make each angle a little bit less than 90 degrees. So we cannot make this happen, right? Okay. So in other words, 3 is okay but 2 is not okay, right? So actually, the best we can do is actually 3 acute angles and 7 acute angles. So 7 acute angle is actually the best we can do. And actually, the graph kind of look weird, but I think you can construct your own graph, but it might be something like this. Let's come up with this. So,
way easier way to draw a really successful.
oh, you got a way easier way? Okay, that's good. I hope this is what I. So this is all the acute angles I come up with. 6, 7. That's the answer. Yeah, those are the 3 big angles. Okay, so anyways, this is a little bit tricky. So there's either with the draw. You wanna draw it on the board? It's okay. Just share it with everyone. If you get a really good graph.
It's the right answer.
Oh, okay. I see. Okay. Yeah. Anyways, you're not required to construct it, but like in your mind, you should be like. Okay, so. Yeah. So this is actually we have a lot of rooms, right? So to take the average amount of degree, it's only like 50 something. So we have a lot of room to work on this. Not a problem. Okay, so next one is on page 184. So, okay, sorry, we're not done yet. So it's, the last problem is actually 5.02.
Where?
It's still on page 181. Last problem. Okay, so what's the maximum number of diagonals in a concave nonagon? So it's 9 sides polygon, right? Which can be drawn entirely outside of the interior of the polygon. This is a really weird problem, right? So I have a concave 9-sided polygon, and you want to have the maximum number of diagonals that are totally outside of the polygon itself. Okay. So what kind of picture do you have in your mind, first of all, when you first look at this problem? You want to draw it?
And like it's like it's
okay.
this, but like
okay,
it's
yeah.
better.
Actually, I can't do not really use. I'll just use your. Yeah, but you can think about it. It's actually something like a cone, right? It's like the size like that, and then finally these 2 big sides will join each other. Something like this. Okay. So there's one side there, and there are 7 sides in between. Right? Something like this, right? Okay. All right. So then that will make the maximum number of polygon. I mean the diagonals, right? Because in between all these points, like in the middle, we can connect all of them 2 by 2 to get the maximum number of diagonals. So how many diagonals are there?
7 choose 2.
So 7 choose 2.
No, because like you can't have them next to each other.
Yeah, if you're saying 7 choose 2, you're just taking 2 points from these 2 and connect them. But actually, if they're adjacent one, they can.
I do not exist.
What's that?
So like 21.
It's like 21. How do you get 21?
6 plus 5 plus 4 plus 3 plus 2 plus 1.
6 plus 5 plus 4 plus 3 plus 2 plus 1. Yeah. Does everyone agree?
It does? choose 7 choose 2 is no.
Okay, so if you pick this point, right, the leftmost end point, how many different diagonals do we get? Starting from that point. So we cannot connect it to the second point, right? So we should start from the third point, and the fourth point, and fifth, etc. Right? So how many points are there? So there should be 5, right?
There's 8
for the first point.
Oh yeah, 5 for the first point, but there's 8 points.
Oh, there are 8 points. Yeah. Sorry, there are 8 points in total. This is a nice point. So you're right. So we should start with 6 because you cannot connect to the second point. So that's not counted as a diagonal. Yeah, it cannot connect to itself. So you're excluding these 2 points, and then you're starting from the third point. So it should start from 6, right? And then you look at the second point, and so on. So you're going to have 6, 5, 4, 3, and 2. The right answer is 21 for this.
AK 72.
And they're all outside of the. So remember, the polygon is here, right? So all these diagonals are outside of the polygon side. This one is a little bit tricky. So if you don't work this out, don't feel too bad, okay? Because the AMC problems are not quite like that. So this just gives you like a taste of some. So it could be like some weird problems about the polygons. So next one is on page 184. We have so 5.120, right? Okay, so we know that in parallelogram ABCD, we have so let me just draw a graph here. So AC is twice the length of BD. So let me draw it this way: ABCD. So AC is twice BD. And then the parameter of the triangle ABC is 21. Okay, so for ABC, the parameter is 21. And then the parameter of BCD is 17. Right? So BCD has parameter 17. Okay, so we're asking about what's the parameter of the parallelogram ABCD. So parameter of ABCD. Okay, so how do you do this one? You can set up some unknowns, right? Then try to solve them, right? So for example, AC is 2BD. So if you write down like AB plus BC plus AC is equal to 21, right? For the triangle ABC. And then for the triangle BCD, we have BC plus CD, which is the same thing as AB, right? And then plus BD, right, equal to 17. And then you realize, well, AC is 2 times BD, right? So this is 2BD. So if you just subtract off these 2 equations at the same time, you're just going to get BD directly. So BD is going to be 4, right? So in other words, BD is 4, AC is 8, right? Okay. And then what?
And then you subtract the BD. Since you know what BD is, you subtract the BDs from the triangles. From those triangles, right. and then
exactly.
You can add BD and BC.
Right. So you can plug in either BD or AC into either of these 2 equations, right? If you plug in BD equals 4, so this is 4, then you have BC plus AB equals 13, right? Okay, and then you realize what is BC plus AB? Well, that's 1/2 of the parameter of the parallelogram. Right? Then just multiply by 2 and get the answer. You could also plug in AC into the first equation. You can also get AB plus BC. Something. This one is straightforward. Okay, so next one, 5.320. Okay, so we have the midpoints of a quadrilateral ABCD. So any quadrilateral ABCD here. So if we connect all the midpoints, right, you form WXYZ, which is WXYZ. Okay, so if the diagonals AC, so if the diagonals AC is 10, so AC is 10 here, and BD is 8, BD is 8. So what's the parameter of the quadrilateral WXYZ? So how do we do this kind of problem? So we have AC is 10, we have BD is 8. That's all we have, right? For the original parallelogram. So they're all midpoints, right? So if they're all midpoints, then what do we know about, for example, ZW and BD? If Z is a middle point of AD, W is a middle point of AB. Yeah, so this is basically, we know that ZW must be parallel to BD, and at the same time, we know that the length of ZW is 1/2 of BD. And that is because of what? Similar triangles, right? So if you have a triangle here, any triangle ABC, if you take the middle point of AC and AB and connect them together on DE, we know that the triangle ADE is similar to the triangle ABC, right? So if they're similar to each other, then basically they're all in proportional, right? So the base side DE here corresponding to the base BC in the big triangle. So DE divided by BC is the same thing as, so the length here AE in the small triangle divided by the length AB in the big triangle, which is 1/2. Okay, so same thing here, although it's in a quadrilateral, you still have the same relationship here. So we have ZW is 4 basically, right? So that is also 4. So what about YZ and WX? So they're going to be 1/2 of AC, right? So AC is 10, so that would be 5. That would be 5, right? So just the parameter would be just 4 plus 4 plus 5 plus 5, which is 18. Yeah, I think it's, yeah, it's a parameter. Area will be a totally different story. Okay, so area, I don't think I can do it. Yeah, but parameter is very easy. Okay, so this one actually used the similar triangles of these triangles inside. You think about the problems about quadrilaterals or parallelograms are often transformed into the problem of triangles. Okay, so that's actually one thing. When you look at the problems actually later, the area problems, and most of the times when you're asked about a quadrilateral, it's always related to a triangle somewhere. So let's see, next one is, oh, so how many regular polygons have interior angles of integral measure? Yeah, so how many, how do you do this kind of problem? How many polygons are there? So ask about the side, the length of the side, right? Or how many sides are there, right, for a polygon? How many polygon have integer value, interior angle? Does anyone have the answer already? So first, any thoughts? So I can use some English here. So yes.
So I think all you have to do is find the factors of 360 which are greater than 1. That are greater than like 60. Yeah.
Okay. So how do you get that? Why are we looking at the number 360 here?
That's wait, no, not 360.
That's okay. We can start together and see what we have like. So first of all, for any polygon with n, a regular polygon with n sides, right? So what are one of its interior angles? So we know that the total amount we have n minus 2 times 180, right? And then if it's a regular one, you divide this by n. Right? So we can simplify this a little bit, right? So this is going to be 180 n minus 360 divided by n. And just multiply everything out. And then just divide this. So we got 180 minus 360 over n. So now you see a 360, right? So what do I want? I want this to be an integer, right? So I want this to be an integer. Okay, so now it's pretty clear what should we do, right? Because when is this an integer?
When it's a factor 180.
Yeah, 180 is actually already an integer by itself, right?
I mean,
so yes, minus that number. So I basically want this number to be integer. And this number is integer if and only if n is a factor of 360, right? Okay, so now the question is, how many factors, different factors does 360 have? How many factors?
No, wait, how many? Oh, okay.
Yeah, does 360 have?
22. Because you subtract 2 is 22.
Yes, that's right.
Just like that.
So the first question, how many factors does this have? If you just answer this question, the answer is 24, right? How do you get 24? Or in general, if I just throw you any number, yeah, if I just give you any number, how do you find out how many factors?
You find the prime.
Yes.
You add 1.
So that's a very powerful tool called prime factorization, right? So for any number, the prime factorization is unique. Right? If you get that prime factorization, you actually knows a lot of information about that number. Okay? So what's the prime factorization for the number 360? We have, I think it's 2 to the power 3, and then you have 3 to the power 2, and then you have, what else you have?
5 to the power 1.
5 to the power 1. Yeah, if you just want to double check, that's 8, that's 9, that's 5. Right. So if you just multiply them together, you get 360. Okay, so then the number of factors actually we're computing here is including 1 and 360, right? So including 1 and 360 itself, there is a total of how many factors? We have 3 plus 1, the power plus 1, right? So 3 plus 1 times 2 plus 1 times 1 plus 1. So that's the number of factors. It should be 1. I just don't want to erase it, basically. Which is 24.
Approximately 24. But yeah, that's true.
Okay, so then we can't keep all of them, right? So which one should we drop?
1 and 2.
1 and 2, why? Why should we drop 1 and 2?
Because you can't make because you can't have a polygon with a negative amount of sides or
Exactly.
0 amount.
So the amount of sides, we should start at for at least 3, right? So you have 3 sides, you can form a polygon. But if you only have 1 or 2 sides, it's not a polygon, right? So the correct answer should be 24 minus 2, which is 22. Okay, so this is a pretty good problem because it also checks your understanding of the prime factorization of a certain number and how many factors are there. Okay. Okay. So that's 520. The last question. Sorry, 720. So again, we have a quadrilateral WXYZ. And we have the middle point, right? And if we connect all the middle points, you get a rhombus, right? Which is even better. So we know a lot of good property about the rhombus here. So these are, yeah, these are PQRS, right?
You can be as specific as
Okay. Yeah. So if the parameter of PQRS is 18, so we know the parameter of PQRS is 18, then tell me immediately what do I know?
you know that the side length is
I know the side length,
9 over
right?
2.
Is 18 divided by 4, which is 4.5 or 9.
Approximately 4.5.
Yes. So it's exactly 4.5, right? Centimeters. And what do you want? So you want the you want the length of the diagonal WY, right?
Similar triangles.
Yeah, similar triangles. So what is WY?
WY is 9.
It's 9. So it's 4.5 times 2, right? So up to this point, you should be very quick. If you have two middle points, then you know that it must be 1/2 of WY. So that's actually a very easy problem. Okay. Questions? Okay. So today we're just gonna go over some very commonly tested materials. Yeah, we're probably gonna go through the problems at the end. But let me first
Geometry practice, right?
just go through some materials with you really quick. All right, so first question, for some commonly used right triangle, Pythagorean theorem. So what are some of the most common sides in your mind? They talk about the right triangle.
4, 5.
3, 4, 5, right?
1 root 3, 2.
That's not a very common one, but yeah, that's good.
No, but that's actually very common.
Yeah, that's right. I'm surprised that's the first triangle to come to your mind. Do you have another one?
1 root 2.
1 root 2.
I
also
forgot what the
very
1575.
So why are these common?
8.
Because this has very special angle, 45 degrees, and that one is 30.
60, 61. Oh yeah, that's true. That's true. On the sprint round. On the sprint round. 1160. On the sprint round.
So actually, another commonly used is 6, 8, 10.
No, but that is the 3, 4, 5. That's
Yeah, that's basically a 3.
Okay, 60, 61, and 11. Yeah.
So we have 11, 60, 60. And we have some other ones, like 9, 40, 41.
8, 15, 17.
8, 15, 17? Yeah, that's a good one. Okay, that's good. So I'm just trying to check if you're familiar with all the regular, most frequently used right triangles. So it turns out these two are very special, right? Because they have special angles. And all the others, if you look at so those are pretty special. Right?
We forgot 7, 15, 7,
Which one?
24, 25.
Oh, 7, 20, yeah, that's another one. 7, 24, 25, and then we have 5, 12, 13, right? So did you see any pattern here? Did anyone? So what's common between these set of numbers?
There's this weird formulas you can use to
What formula?
it's like the smallest side for a right triangle is n, and like the next smallest side is n squared minus 1, and then the next one is like n squared plus 1. What? It's something that I heard.
Okay.
It's weird.
All right. So first of all,
Wait, no, but
the smallest number
there's
among
only
all
1 root
these.
2
Sorry?
root 3 triangle.
The what?
The 1 root 2 root 3, and then there's also the root 2 root 3 root 5. And then the root 3.
That's right.
And then the root 3.
You can make a lot of triangles just by taking the roots.
There's the pi. There's the 1 pi, and there's a pi and 2.
I think what's common about these set of numbers is the smallest number is always a odd number, right? So we have 5, we have 7.
No,
we have
no,
9.
8, 15, 17.
8, 15, 17.
Yeah.
Yeah, no, I'm just trying to look at like what's similar in between these set of numbers, right? So then you can see that, and the other similarity is between the second largest and the hypotenuse, they only differ by 1, right?
15 and 17.
So for these numbers, actually, they have very good properties. So suppose I ask you, what is 13 squared minus 12 squared? It's funny, how do you get that so quick? No, not from there. I'm asking this. So in general, if I ask you what is n plus 1 squared minus n squared, how do you get it quickly? Because you have x squared minus y squared is x plus y, x minus y. And then this x minus y is always 1 because they differ by 1, right? So this thing is gone. So it's only just 2n plus 1, right? Okay, so same thing here. So what is 25 squared minus 24 squared?
49.
49. You're just adding up these two numbers. So what about 61 squared minus 60 squared?
121.
121. And what about 41 squared minus 40 squared? Okay. And another good thing is these are all perfect square numbers, right? So this is 9 squared, that's 11 squared, that's 5 squared, that's 7 squared. Right? So if you have that in mind, you can maybe construct a lot of triangles that looks like this, right? So the second longest one and the hypotenuse differ by 1, and then you're trying to find a complete square for the ones. If you add them up, you get a complete square. But that's just something that may or may not help you in the test. Just
Which test?
not bad to know. Oh, the AMC test, of course. Okay. Oh, and then these we just mentioned the special right triangle. We have 1, 2 square root 3 and 1, 1 square root 2. Right. These are
And
the.
also like the 1 root 2 root 3, and then the root 2 root 3 root 5. Root 5 root 8.
All right. So. Yeah, I'm trying to think about. Okay, and then everyone learned know about the distance formula, right? So it's in a coordinate system.
It's just the Pythagorean theorem.
Exactly, just the Pythagorean theorem inside just using the coordinates, right? So if you have one point A, which is x1, y1, another point B, x2, y2, then what's the distance between them?
X1 minus x2 with the absolute value of that squared.
So it's
plus,
just that square plus
y1 minus y2
y1 minus y2 squared,
and then you square root the whole thing.
Now take a square root, right?
Which
Okay.
is just Pythagorean theorem.
Yes. So the order doesn't matter. It could be x2 minus x1, x1 minus x2. Doesn't matter because when you square it.
Find the absolute value.
Yes.
Well, actually, you actually don't need to.
You actually don't have to
square
because when you square it,
Squares are always
you get a positive anyways,
unless
right? So it could be as value, it could be just bracket. All right. And then once you look at one problem about the area, actually we're going to see a bunch of them, but this one is kind of special. Okay, so you're asked about what is the area of the circle? What is the area of the circle that is inscribed within a triangle of area?
So it's the in circle?
Yes.
What page is that on?
This is page 206. The example, the last example on page 206. So we want to have the area 30, and then we have the parameter 30 as well.
So what is the area of the in circle?
Okay. It seems like you're not given a lot of information. Just know the triangle. It has an area of 30, and then it has parameter of 30 as well.
But we know that it, like it could be a 5, 12, 13.
Yeah, could be.
You can use that weird formula that's a sum perimeter times radius of
Oh yeah,
equals area.
yeah, but oh yeah, true.
Which formula?
The semi-perimeter times
Oh,
the
semi-perimeter.
radius of in circle.
Okay, yeah, that's. But how do you get that formula?
What?
So suppose you don't know that formula, then how do you solve this problem?
You assume it's a 5, 12, 13 triangle.
It actually could be.
Yeah.
Could be.
Okay.
So
Since it's a math problem, you can be any triangle as long as it's friendly.
Friendly, okay. Okay, so the way is actually you try to break this up, right? So if you have a center of this circle, if we connect the center, let's call it O, connect OA, OB, and OC. Okay, so what can you say about these three triangles? ACO, ABO, and BCO. Yes.
the sum of the areas equals the area of ABC.
Yes.
Good job, Daniel.
Anything else?
You get it.
Yeah, if you add all these, well, that's very important. Actually, that's what we're trying to use here, right? If you add all these three areas, you get area of ABC. And ABC, we already know the area is 30, right? So we have something on the right-hand side already. But what about the left-hand side? How do you set up the equation?
AC times radius divided by 2 plus AB times radius divided by 2, and you get the idea.
Yes. BC times the radius by 2, and then we have AB times the radius by 2. Okay, because all these are
Oh, yeah.
perpendicular, right? Okay. And then you can take out a common factor, 1/2 R, right? R is the radius. And then what's left is the circumference, which is AC plus BC plus AB, we already know it's 30, right? So that's 30, and then plug in, you get R equals 2. Right? Okay, so then you can get it. Okay. Okay, so let's look at some real problems from the AMC. I'm not sure if you have a time to finish off it. So does everyone finish this?
Yes.
Yeah.
Okay. So most of them are pretty easy, right? So there are a couple of them that's a little bit tricky. Okay, so we start with the first problem. We have three triangles, so that one is pretty easy, right? So we have ABC, ADE, and then EFG, right?
Oh, that one was fun.
Okay, so all of them are basically D is the middle point of AC, G is the middle point of AE, and so on. Right? So then we know that AB is 4, so these are all equilateral. So AB is 4. And then you're asking about what's the parameter of this figure A, B, C, D, E, F, G, right? So A, B, C, so it's A, B, C, D, E, F, G, and go back to A. Okay, so that's very easy. So we just start from A, we get 4, and then BC is another 4, then we get 2, right? Then we get another 2, then we have 1, 1, 1, right? So just don't forget the last one, AG is also part of this figure, right? So a lot of people make a careless mistake over here. So the answer for this one is 15, right? Is that 15?
Yeah. That's not
8 plus
15,
4,
it's 15.
oh yeah, it's 15, yeah. All right, let's see the next one. We have a isosceles right triangle.
Okay, and there's like a ton of nice properties.
Yeah,
Right.
like the circle described in it basically gives you the answer.
Okay, so you have half of a circle describing it, right? So,
You actually could just draw like the other half of the square and then it becomes really easy.
okay. Yeah. Just trying to make a good picture. Okay, so isosceles right triangle ABC enclose the semicircle of area 2 pi. So you already know the area is 2 pi, right? So what do we know about the radius? So radius is equal to, so we know that half pi r square equals 2 pi.
Radius is
So radius equal to 2, right? Yeah, so plus. And then you ask about what is the area of the triangle ABC, right? So what is it?
8.
So it's going to be 8. Why is that?
Because so if you draw the other half of the square, the circle's diameter is just the square's side length, which is
right.
4, which is 4. So then 4 times 4 is 16.
So
and
4
then
times
1/2
4
times
is 16.
is approximately
1/2 times 16. Okay, so next one. I'm not sure if I want to have the same page. I got the next one is like we have a triangle here, and then you have an inscribed triangle with all the middle points A, B, C, D, right?
Is that what how's that a triangle?
Oh, no, I mean a square. I'm sorry. The inscribed square here. Okay, so if the larger square has area 60, the area of the larger square is 60. You ask about what is the area of ABCD, right? So what's the answer for this one?
6, 20, 30.
So area of ABCD is 30, right? So how do you get 30?
60 divided by 2.
60 divided, not 60. How do you know it's 1/2 of
Draw
the?
AC and
Because so if so 1 it looks like it,
Okay.
and then 2 so if you mark the points on the
Also do
the
that.
end of the square, so like that all the triangles are congruent
Yes.
because of ASA.
Yes, ASA, right? Or you can just cut the middle through into 4 triangles. It looks like these two are the same, these two are the same. So then this will take half of the area. Yeah, so that's very easy. Okay, problem number 6. So we have a T-shaped rectangle, right? So that's about its parameter. We have 2 2x4, right? So these are, that's 2, that's 2, that's 4, that's 4, that's 4, that's 2, right? So what's the parameter? Well, just adding them up, right? So 4 plus 2 plus 4 plus 2 plus 4 plus 2. Right? So the answer is 20. Okay, so next problem is a little bit tricky. So it's problem number 25. I forgot the year. I think it's 2003 or something. 2003 or 2002. I forgot. So the problem is we have a square of length of length 2. Okay? So 2 by 2 square, and then we have a circle.
Weird circle.
Yeah, circle kind of cuts through.
You don't do that. We found out that the area of the circle is equal to the area of the square.
It's a really bad circle, but just pretend it's a circle. Okay. Okay, so it's a pretty drawn circle, but okay. Anyways, so we have something like this, right? So it's it's a square with side length 2, and the circle share the same center. So they all share the same center here. So total area of the regions that are inside the circle and outside the square. So which part is the area? Which part is the region inside the circle, outside of the square?
The round things outside of the square.
Right. So the round thing here, the round thing here, round thing everywhere. Here. And by symmetry, actually, it's 4 times any well.
And then we discovered that the circle's area is equal to the square area.
Yeah. Okay. How do you know that? Okay, so because let's finish reading the problem. Okay, so we have this part. This region has the same area as the regions that is outside of the square and inside of the circle. Oh no, I mean outside of the circle and not inside of the square. So which are those parts? Right? Use a different color. So these are the area that is inside the square but outside of the circle. Right? Triangular thing with a arc as the hypotenuse, right? Okay, so these 4 areas, if you add up all these 4 areas, if you add up all these blue areas, they are the same. Okay, so then you're asked about what is the radius of a circle? So how to do this kind of problem? So the square, we know that it has length 2, right? so length of a square is equal to 2. So first of all, how do you know the area of a circle and the square is the same? Yes.
So the blue and red thingies are the same, have the same area.
Have the same area, yes.
And they both share that.
The white thingy.
Okay.
The blue dot in the middle.
So they okay, I see what you mean. So you're saying that they all share the green part, right, in the middle, basically.
The green stripe.
Yes.
Green stripe. The green oval square.
Right. So if you think about it, if you only look at the green one at the 4 red corner will give you the square, right? And then the green one at the 4 blue parts will give you the circle, right? So if these 4 things have the same area as these 4 red things, then you can get actually the area of the circle is the same thing as the area of the square, right? That's easy, right? So you just need to make this observation basically. Then we know that, so it's 2 by 2, so it's the area of the square is 4, then this is pi r squared, so r is square root of 4 over pi.
Which is actually 2
Or
pi over pi.
Yeah, 2 root pi over pi.
Oh yeah. The area of
Oh wow, this one was actually really easy.
Okay, so another, okay. The next problem is you have a polygon A, B, C, D, E, F. So we have A, B, C, D, E, F. Okay. Then you're given some lengths. We have, so AB is 8, that's 9. AF is 5. And you know the area of this thing here. The area of this thing is 52, right? So area 52. So you ask about what is DE plus EF. So D is that, EF is this, right? So DE plus EF. Okay, so first of all, one of them is very easy to get, right? Well, what is DE?
4.
DE is 4, right?
4
Because it's just not, yeah, 9 minus 5 will give you 4. So what about EF? How do you get EF?
Because the area of ABCDEF is 52, and then B times 9 would be the area of the whole thing, so FED, and then that other imaginary point was like actually like.
It's like if you extend AF and then CD, you get a point called Z.
And then that would be 72. So and then you do 72 minus 52, and then you eventually end up with 20.
So this is so the imaginary point is very important, right? In MCA, you need to have a lot of imaginary points.
And then 20 divided by
So this one is pretty obvious. You just need to extend these two lines to form a square, not square, rectangle. So then you have the big area would be 8 times 9. The smaller area they're given is 52. So this is 72 minus 52, which is 20, right? So 20 is this smaller one. So you have D times EF is 20. So EF equals 5, right? So the answer is 9. So the next one is trapezoid. So trapezoid is also very commonly tested because it can test you on, first of all, the area of the trapezoid, the formula, right? And also it's often related to the Pythagorean theorem, right? Because you have to figure out a lot of parts by yourself. So let's look at the next one. So we have a trapezoid ABCD. So the trapezoid ABCD looks like this. Okay, so you're given some of these lengths. So we have BE is 24, AB is 30, BC is 50, is 25. And you ask about the parameter of ABCD, right? So it looks like we already have AB, BC, and CD. The only thing that's left is AD, right? So how do you get AD?
Draw an altitude from C to AD.
From C to AD, yeah. Let's draw a perpendicular line, right? To make your life easier.
Which would be equal to 24.
Let's call it Z again. Right, so Pythagorean theorem, 2 of them, right? So one from here, one from there. So what is AE?
AE is 18.
18, right?
Because of the because of 3, 4, 5 triangle, you inflate it 6 times. Yeah.
Right, and then what about EZ?
7.
Right?
Just practically.
So this one would be 7 plus 18 plus 50, right? So 50 plus 18 plus 7 will give you AD, which is 65, right? So then parameter just yeah, 60.
part is
65.
Yeah, make it
70, no, it's 70, yeah, 75.
Oh, 75.
all right.
You can't do math. Okay. So the answer should be 180, right? So 75 plus 30 plus 50 plus 25. Okay, next page. We have a okay, so we have ABCD as a rectangle. So ABCD is a rectangle. And EFGH is a parallelogram. Just picking some random points and form a parallelogram. EFGH, right? Okay, so use the measurement given. What's the length D here of a segment that is perpendicular to both HE and FG? So basically drawing a segment here that's perpendicular here and there, right? Being a parallelogram, and you're given these measurements. So you have 3, 4, 6, 5, 3, 4, 6, 5. Okay. And you're asked about what is D. So before you tell me the answer, what's the approach here? How do you get D?
You get D by the area formula.
By the area formula, right? So basically, we know the area of the rectangle is easy to compute, right?
And then the area,
And the area of these triangles are also easy to compute. Yes. And then after you take off these 4 triangles, you get the area of the parallelogram. And then you can figure out the height, basically, right? So that's a plan, right? So whenever you do a geometry problem, you always should have a plan in your mind first, right? If you have that plan, then the rest is easy. You just carry out the calculation, right? Okay, so first step, we need the area of the rectangle here. So it's going to be 4 plus 6, 10 times 8. Yeah, so it's 80. So what about these 4 small triangles?
the small triangles, the 3 by 4s are both 6, and the 5 by 6s are both 15. The area.
Right. So basically multiply by 2, right? So these will cancel. So just get 12 plus 30, which is 42. Right? So take that off. So get 80 minus 42 equals 38. So 38, remember, is area of the parallelogram. EFGH. Right? And then you use the
For the base.
yeah. You need to use Pythagoras theorem for the base, so which is 5, 3, 4. Right. Very good number. So I have 5 times D equals the area, which is 38. So D is 38 over 5, which is 7.6. Okay, very nice. Next problem. Okay, so next one is you have a 2 4 by 4 squares, right? So 1 4 by 4 square, 2 4 by 4 square intersect each other, and you put a circle in there somehow. Just to make your life harder, they put a circle here. Okay, so sorry. Okay. Just make this a little bit bigger. Okay, something like this. Right? Okay. Okay. Okay, so they intersect at right angle. So this is a right angle basically. And it's bisecting their intersecting sides as shown. And the circle's diameter is the segment between the 2 points of intersection. So we have the so this one here, between these 2 points, you get the diameter of the circle. Right? Okay, so what's the area of the shaded region created by removing the circle of the square? Okay, so basically you only want this part plus that part. Okay, so how do you do this kind of problem? So what's the plan again?
We find the area of the squares and
The area of square is easy, right? 4 by 4. So you get 16 is the area of each of these squares. Right? And then what's the next step? Yeah.
Find the area of the circle.
Of the circle. How do you find the area of the circle?
R squared pi. That's the area of the circle.
So pi r squared is the right answer, but you need to form something before you
You need to form the intersection of the squares.
Yes. So that's intersection of the squares, right? And they're perpendicular to each other because it said so, right? So this angle is 90 degrees. That's also 90 degrees. So this is also a square, right?
So that's a 45, 45, 90 triangle.
and then 2 2.
Yeah, right. So this is a middle point. So this is 4, that is 2.
You are, and
Then we know the hypotenuse would be 2 squared 2, right? So 2 squared 2 is 2 times r. R is square root 2.
and then you do root 2 squared pi.
Right. So get the area of a circle, which is what? 2 pi, right? So pi r squared is just 2 pi. Okay, so now you get the area of the square, you get areas of circle. What's the next step?
We need to get the area of overlap.
So we have to be a little bit careful here, right? So what's this and that? So I'm adding up these 2 square first, right? So we have 4 by 4, so we have 16 plus 16, right? But there's something we add twice, right? Something in common. So which part did we add twice?
2 by 2
The
squared.
2 by 2 squared is shared in the middle, right? We added 2 times, so we have to subtract one of them, right? So what is one of them is 2 by 2, right? Which is 4. Yeah. And then what else do we have to take off?
Nothing.
So what is this? This is this square plus that square minus the middle. So this is basically everything here, right? Including the circle. Right? I'm only counting the middle part once. So that's going to be everything inside here. But then I still have to take off the circle, right? So then I have to minus 2 pi. Right? So when you're counting, just be careful. Okay, there's a lot of things involved here. So there's double counting for the middle square, and then don't forget you still have to take out the circle. So it's going to be 28 minus 2 pi, right? So you can see this problem is not really that hard, right? If you draw the picture correctly. And I think the last step is a little bit tricky because you have to think about a lot of shapes in your mind. But besides that, there's nothing really difficult here. Okay. All right, so next question, we have a parallelogram again, quadrilateral again, sorry, ABCD. Put the words together. So we have ABCD, and then we have AB and BC are the same. And then we have CD and DA are the same. So what kind of thing do we call this? If they have these two are the same, that two are the same. It's a kite, right?
A piece of
So what properties do we have for a kite? What special properties?
The
Angles are perpendicular.
Two of the diagonal are
diagonals are perpendicular,
perpendicular
and
to
then
each other.
B and then BD will perpendicularly bisect AC.
Perpendicularly bisect AC. Okay.
It's super perpendicular.
Okay. And then when does AC bisect BD? When does AC bisect BD?
When it's a kite.
When it's a rhombus, right? When it's even better kite, so it's like a symmetric kite everywhere. Then they're gonna bisect each other, right? The diagonals. But if you only have a kite, then only AC got bisect, not necessarily. Okay, so then what do you know? You know A, B, B, C are 10, and you know that C, D, D, A are 17. And the measure of the angle ADC is 60 degrees. So we have ADC, this angle is 60, right? So what is the length of the diagonal AC? There are a lot of ways to do it, right? So how do we get AC?
17 because of the equilateral triangle. 60 triangles. Because 60 triangles.
Right. That's very good, right? You notice that this is an equilateral triangle. Because CD is AD, that's 60, so they're almost 60, right? So then you already get it 17. Is there another way to do it?
Yes.
Yes.
You find angle ABC and then you solve cosine.
Yeah, you can use.
Yeah,
you
but
can use
like,
trig
but
function
like,
to do
it's
it, right?
actually hard.
That's another way to
Well,
do it.
actually, I learned it like today.
Okay. Yeah, so anyways, since there are a lot of ways to do it, but this is probably the easiest way, right? You just
Actually,
okay, so let's look at the rest problems really quick.
Problem 6.
Number 6 is easy, right? You don't have to.
It kind of looks like a right triangle.
yeah, kind of look at the right triangle.
The area of the 3 squares, we have 169, so the side is 13, 5, and 12, right? So that's the right triangle here. So then, of course, the area is going to be 1/2 times 12 times 5. So it's 3.
Whoa.
The next problem. Next problem is looks very complicated, right? But it's actually pretty easy. So first of all, we have a square. So we have WXYZ. And then we have some small squares here and there, right?
But like, no, it's not.
Yeah, go ahead. You can go ahead and use the restroom while I'm drawing this picture.
But like, are you allowed to or not? That question is, are you like,
Okay, so we have the area of WXYZ, so it's a square. So the area of that is equal to 25, right? So then you know that this is 5, they're all 5s, right? Okay, and then we know the 4 smaller squares has side 1 centimeter each. Okay, so these 4 small squares each have 1, right? For the side. Okay, and then we have AB is equal to AC, right? So it's these here. As you know that when ABC is folded over BC, so suppose you're folding this the other side, then we know that the point A will coincide with the center of the square WXYZ, right? So in other words, when you fold it over, it looks like this, right? Yeah, that's it. So what's the area of this triangle ABC here?
It's around 27/4.
So how do you get the area?
So you use a 1/2 base times height.
So
Yes.
BC
So what's a base? BC is,
BC is approximately 3.
so it's 5 times 1 times 1 from each side, right? So it's going to be 3, right? So what about the height? The height here?
And then it's and then so it's 5.5 because you reflect ABC and then you got like the O, so then you
Right,
get
so it's
the 1
basically-
plus 5. I mean 2 plus 5, which is approximately
2 plus 5? Really? 2 plus 2.5. So this is half of that, right?
Wow.
So you have 2 plus 2.5, which is 4.5.
Yeah, 4.5, which is also 9/2.
Yes. So then the area would be 1/2 times 3 times 4.5.
But like using approximately 9.2 is better because the
No, but
integral fractions.
Yeah, it's true. So it's 27/4, right? Yes. So next page, the trapezoid one, I won't go over again. It's very easy. You can do it yourself, okay? I'll just give you the answer for that one. So problem number 21, the trapezoid one, the answer is B. Okay, so it's problem number 21. And problem number 22, what's the answer? So it's C, right? So the area for the first one is, for A is 4 minus pi, right? And for B is how much? Also 4 minus pi, right? And for C is pi minus 2, right?
And since pi is approximately 3.141.965 pi, 9793338 plus x.
That's you do it right. So I know that pi is a little bit bigger than 3.14, so you can see this is the biggest one. Okay, next problem. What do we use? Problem number 20. We use a similar triangle again, right? A similar triangle, if you want to use, if you want to find the area of the shaded region, how do you do it?
You find the area of XYZ and then you subtract XA and then the intersection of AB and X.
Very good. So area of XYZ minus the area of XAB, and then divided by 2, basically, right? Because of symmetry. So the answer is D, right, for number 20. And the next one is, again, Pythagorean theorem. So the correct answer is E, right?
Yay.
So that's why it goes Z. 24 is, I want to go. So we have A, B, C. You see a lot of things are actually not useful here. So you just need to focus on the right triangle. That's all you have to do. Okay. So for this one, we know that so the angle A is 20 degrees, and then we have AFG is AGF, right? So basically AG and AF are at the same length. And they're asked about what is angle B plus angle D? So it's 80. How do you do it? So which triangle should we look at for this one?
AFG.
AFG, yes.
GAF.
Yes, so AFG, so basically we can get these two angles, right? Because it's isosceles and the top angle is 20. So we have 180 minus 20 divided by 2, which is 80, right? So these two are 80. And then what's the next step?
You find that, you discover that DFD is 100.
No, you
Yeah.
discover that AFG is the external angle of triangle BFG.
Exactly. You just look
Actually,
at the
easier to
triangle.
find the
Yeah.
VFG because then you find the
Yeah,
one
either way.
location.
I mean, you either find out this angle is 100 degrees, or you can just use that is the external angle of the triangle BF.
And then you discover
So
that
B
the
plus
answer
D
is
would be just 8.
No, and you discover that the answer is approximately 8.
Okay. So next problem is yes, 27. How do you get it? A, B, C, D.
Complementary counting.
Really?
You actually are.
We're counting the numbers for units.
Okay, so ABCD has area 72. If point A and the middle points BC and EC are connected to form a triangle, then the area of the triangle is how many? So ask about the area of the triangle. So again, it's like you take off all the 3 triangles here from the big square, right? And then you can get the area of the triangle. So we know that, suppose this is x, that's y, so we know that x times y is 72, right? That's the area of the big rectangle here. So what about all these 3 triangles? So we have x, this is y over 2. I mean, this is y, sorry. This is x over 2. That's another x over 2. This is y over 2, y over 2. So the first triangle has area 1/2 x times y over 2, right? And this one has 1/2 x over 2, y over 2, right? And that one has 1/2 y x over 2. So if you add them all up, what do you have? So this is over 4, over 8, over 4. Xy over 4, xy over 8, and then xy over 4 again, right? So it's going to be xy over 5 xy over 8. Okay, so 70, you know that xy subtract off that will be the area of the triangle, right? So we know that what we want is xy minus 5xy over 8, which is 3xy over 8.
So it's 38 times 72.
Right, so then you're just plugging that is 72. So it's going to be 27.
Approximately, oh yeah. Approximately 27. And then, wait, yeah. Approximately 50. The next column. Approximately 50.
Okay, so problem number 19. I just finished this last problem. Okay, so we'll give the rest answer to you directly. So we have 3 circles of radius 5. 3 arcs are pieced together like that. Okay, so arcs AB and AD are quarter circles. So these are quarter circles. Right? So this is AB, that's AD. And BCD is the top circle here. So what is the area of this region? So again, you need some.
49.94.
Right. So how do you do that? You need some imaginary points, I guess, right? So first of all, you connect BD. So get a half circle here, right?
Also,
That's easy. So what about this part?
you can draw the line parallel to BD that contains line A.
You draw a line here and then connect. So why does that help you?
Because then you get to connect the quarter circles.
Exactly.
And then,
These are the quarter circles, right?
And then
And this is a rectangle, which is
you can just flip the quarter circles. And then you could just do the rectangle minus the quarter circles.
yes.
Yeah, and then
So up to this point, you can do whatever you want, right? But the thing is, you have to have this in your mind, okay? So the half circle is how much? The area of the half circle is 25 over 2 pi. And then what about the rectangle? Rectangle is, what is that? 10 times 5, right? And then you minus 2 of the quarter circles, which are,
So the quarter circles are congruent to the thing. So it's just the area of the rectangle.
exactly. So these two will just cancel, right? Because if you piece these two quarter circles together, you get a half circle, right? So these two will cancel. So basically just get that. So just get. Okay, so next page, I think I accidentally put the same problems. I'm sorry about that. And number 13, the answer is A.
Oh, there.
And the last problem, the answer is A, number 6. Okay, so these should be easy problems. Okay, so sorry for the delay again.
It's C, right? C is, right?
Number 13?
Wait, C. No, RTC is 36. CRT is 72.
Okay,
Yeah, because like,
so the answer should be C.
then you find like the.
Thanks. I think I found the wrong. Okay, so very good. And I'm going to assign some homeworks, unfortunately, to you. And first of all, I want you to finish reading of 5.3 and 5.4. Just the reading part, including the examples and everything. So reading 5.3 and 5.4. And then
I'm looking through this area.
This side.
Oh, that one.
Oh, this is the.
Yeah.
okay, so now on page 196, the odd problems. And also page 200, the odd problems.
200 odd problem. So it's like 5.2060.
Uh,
Oh, 5.160 and 5.360.
yeah, just odd ones. And then on page 207,
Okay.
the even problems.
0, 2, 4, 6, 8.
Yes.
9.
So that's it for today. See you guys next week.
Okay. Okay. In approximately 7 days.
Wait, what's the that's right. That's right.
207.
Come on.